Hello, my dear friends. I am Dr. Shailesh Palekar. I am working as an associate professor in the Department of Mechanical Engineering, Sanjivani College of Engineering, Kopargaon. This is our 19th lecture for the subject Dynamics of Machinery for our first unit. That is, our first unit's title is Free Vibrations of Undamped and Damped Vibrations of 1DOF System. So this is our 19th lecture, and in our 18th lecture we have discussed the displacement equations for the three different types of vibrations based on value of zeta, that is overdamped system, critically damped system and underdamped system. When we have seen the case of underdamped system, that time we have observed that the value of the displacement in each cycle of the vibration goes on decreasing, and this decrease in the value of x is exponential one. With that, we will see one new term in this lecture, that is logarithmic decrement, or how much is the loss of amplitude or decrease in the displacement when we will apply the damping conditions. Okay, so the the first term comes into picture in case of damped vibrations, and that too the damping is viscous one. So in that case, the decrease in the amplitude is related by a term known as logarithmic decrement. So in damped free vibrations, two important parameters indicative of vibrations are natural frequency of damped vibration, that is omega d, which we have discussed in the previous lecture, in the lecture number 18, and the rate of decay of amplitude or rate of decrease of amplitude. So the rate of decay of amplitude is measured by one parameter known as logarithmic decrement. The rate of decay of amplitude is proportional to the amount of damping present in a system. The larger the damping, the greater will be the rate of decay. It is it is a case that when we provide the damping, that time the function of damper is what? It should absorb the vibration energy. But how much is the resistance provided? Based on that, the vibrations are absorbed, and that much is the loss of amplitude in each cycle. In case of overdamped system, you have seen that the vibrations, the systems are not performing further oscillations or vibrations. As soon as you apply the force, they will get displaced from the mean position, they will reach to the extreme position, and from that extreme position, depending upon the conditions of damping, that is overdamped or critically damped, they will come back. They are trying to come back to the mean position as soon as possible, but will reach to the mean position, exact mean position, after we can say certain time, or it will take infinite time. But in the case of underdamped system, the system will perform further oscillations depending upon the damping conditions. Means the value of course should be less than 1, but if the value is 0.1, you can easily say that the system will perform more number of cycles as compared to the system which will have the value where we have provided the damping conditions as zeta is equals to 0.9. If zeta is equals to 0.9, definitely you will easily understand, you can say that system will perform less number of cycles. If the value of zeta is zero point 0.1, then as compared to 0.9, the number of cycles will be more in the case when the damping condition zeta is equals to 0.1. Okay, so the rate of decay of amplitude in such cases will be depending upon the damping present in the system. So we can define that logarithmic decrement as, the logarithmic decrement is defined as the natural logarithm of the ratio of any two successive amplitudes measured on the same side of mean position. Measured on the same side of mean position. So here you can easily understand the definition. The logarithmic decrement, how we have defined the logarithmic decrement, is defined as the ratio of two successive amplitudes measured on the same side of the mean position. So here we have shown the amplitudes or displacements of the vibratory systems in each cycle as x1, x2 and x3. If you carefully observe this figure, then this x1, x2, x3 we have marked on the same side of the mean position. Then according to our definition, we could write the logarithmic decrement as this logarithmic decrement we are denoting by delta, and is given as log base 2e, that is natural log of two successive amplitude, that is x1 upon x2, measured on the same side of the mean position, measured from the same side on the mean position. Okay, so it is, we could write this as delta is equals to log base 2e x1 upon x2, or in another sense we can write this equation as 2 pi zeta upon square root of 1 minus xi square. This is also one more expression for delta. When the value of zeta is very small, then above equation, this equation can be written as delta is equals to 2 pi into zeta. These are what the relations for finding the value of delta or delta. Sometimes you have the value of delta, then they might ask you to find the value of zeta, then you can use this relation. If you have the value of zeta, then also you can find the value of delta. So these equations you need to remember properly. We can, and this will help you to solve the numericals or problem based on this concept. Okay, now it is not a same case that in your numerical that they will give you the displacement of suppose first cycle, and directly they have given the displacement of 18th cycle, suppose means system is performing 18th cycles, and they have explained about the initial displacement and the last cycle's displacement. That time how this relation can be used. So let us assume that system is performing n number of cycles. So we can write, in such cases the delta can be found as delta is equals to 1 upon n into log base 2e x1 upon xn. Instead of x2 we have xn, where n is the number of cycles, n number of cycles. So it might be the n value might be 10, 5, 2, 18, like that, anything. So for such cases we can use this relation delta as delta is equals to 1 by n into log base 2e x1 upon xn. Now this is the case of previous cases of viscous damper. If we have the dry friction damping or Coulomb damping, that time the rate of decay or the rate of decrease in the oscillations or cycles can be found as, in Coulomb damping the difference between any two successive amplitudes is constant. The difference between any two successive amplitudes is constant and is given as delta. Here instead of using small delta, we have used the capital delta as a symbol for logarithmic decrement or rate of decay. Okay, so delta is equals to 4f upon k, where f is the frictional force or force applied on the system and k is the stiffness. Okay, and in case of torsional vibrations, this is equals to 4 into T upon Kt, where T is the torsion and Kt is the torsional stiffness. This way we can find the rate of decay, or we can say the log decrement in the amplitude for the different types of dampings we have provided. When the viscous dampers or oil dampers are used, that time the delta or the rate of decay or rate of decrement in the amplitude can be given as logarithmic decrement, and it is delta is equals to, or small delta is equals to log base 2e x1 upon x2, or if n number of cycles are there, that time delta is equals to 1 upon n into log base 2e x1 upon xn will be the relation to find the delta. And if it is a case of Coulomb damping or dry friction damping, then we have to use the symbol as capital delta is equals to 4f upon k. If it is a case of torsional vibration, then it can be written as capital delta is equals to 4t upon kt. So what is this torsional vibrations are? If the torsional vibrations are there, and that too we have used the damping, that time the relations, various relations which we have to use to solve the numericals or problems, how they can be written and what is the difference between them. So let us discuss about that. So the fundamental differential equation of motion for torsional vibration can be written as I into theta double dot plus Ct into theta single dot plus Kt into theta is equals to 0. This is the fundamental differential equation of motion for damped free torsional vibrations. Now, the critical damping coefficient for such cases, torsional vibrations, can be written as CCT. This is the symbol used. Instead of CC, we will use CCT. So T indicate that it is a case of torsional vibrations, and it can be written as, or it can be found as 2 into square root of KT into I, or it is equals to 2I into omega n, where omega n is the natural frequency of undamped free vibrations. Okay, and the damping factor in such case is given as xi is equals to Ct upon CCT. So Ct is what? The torsional damping coefficient, and CCT is critical damping coefficient of torsional vibration, or torsional critical damping coefficient. And the logarithmic decrement, if it is a case of viscous damper, then the logarithmic decrement can be given as delta is equals to 1 upon n into log base to e beta 1 upon beta n, where beta is the angular displacement of the system. That is, instead of writing theta, we will use the beta as a symbol. Okay, so this way all these formulas, whatever the derivations we have seen, we have to apply to solve the numerical based on these particular concepts. In further lectures, we will solve one numerical or problem based on all these concepts. Thank you.